Okay, so our next speaker is Professor Umberto Zannier from the Scuola Normale Superiore di Pisa. So he will speak on, he will speak on bounded generation in anisotropic linear groups. So Professor Zannier was the host of the Indo-Italian number theory meet long back in 2012. And it was really a pleasure to have met him and to have had this interaction, the Indo-Italian. It's a bit sad that such meetings have not occurred after that, but we hope it will start once the COVID gets lifted. Thanks, Umberto, for a very nice meeting in those days. Go over to you for the talk.
Thank you very much for reminding this. It is a pleasure for me to remember. And thanks for having been present on that occasion. And of course, I thank all the organizers and persons involved for inviting me in this conference. I am honored to speak in it. So, as the title says, I will speak about bounded generation in anisotropic linear groups. And the first, let me recall, even if it may be known to most or all, what bounded generation means. First, this is a definition which may hold in every abstract group, and I view it as a strong form of finite generation. So the definition is that a group gamma is said to be boundedly generated BG, if there exist finitely many elements of gamma, gamma 1, gamma r, such that each element of gamma is a product of powers of gamma 1, gamma r in this order. So this is important. So whereas, of course, for being the gamma i's to generate, we can do products of them in any order. But now we prescribe to do in this order, and we allow any power. So this is a strong form. Let me give some examples just to figure out what the notion means. Every virtually abelian, by virtually I mean a group which has virtually with some property, means that there is a subgroup of finite index with that property. So every virtually abelian group, if it is finitely generated, it is also bounded generated. And this is trivial to check. And less trivial, but still true, is that this holds also for a virtually nilpotent group. So these are the first examples of boundedly generated groups. And so nilpotent suffices plus the finite generation. However, for instance, solvable does not suffice together with finite generation. There are examples of solvable groups finitely generated but not boundedly generated. However, this suffices if when we exhibit solvability filtration, if all the pieces are finitely generated and boundedly generated. In fact, an extension of groups with bounded generation has itself bounded generation, which is very easy to check. So this is a second remark. And the third remark, for instance, a result by Malchev, it follows that every solvable subgroup of GLN-Z has bounded generation. So, for instance, for solvability suffices inside such arithmetic group such as GLN-Z. So let me go to our context, which indeed concerns linear groups, gamma, and by which I mean subgroups of some linear algebraic group, points defined over some field K, assumed to be in the whole talk to be of characteristic 0. So let me do some remark on the relevance of the condition of being bounded generated, to see that this notion is may appear perhaps artificial, but it seems not to be the case, because it has been found to have important consequences towards several questions. And among these, I mentioned work by Lubotsky and independently Platonov and Rapinchuk, 1992. They proved the congruent subgroup property, which of course has been studied by many now classical property. And they proved that this congruent subgroup property for certain arithmetic groups and provided the bounded generation holds. So the bounded generation was a crucial ingredient for their proofs. Another result by Shalom Willis, they used crucially bounded generation for proving the Margulis-Zimmer conjecture, which I do not recall, and actually I'm not even familiar, but it is for experts in the field a very, very important conjecture, a bit technical to state, for certain arithmetic subgroups of Chevalley groups. And then another thing that I recall is further implication of the bounded generation appearing work by Avery, Lubotsky, and Meyer. Let me give some examples of when bounded generation holds. For instance, landmark result in this topic is Carter-Teller, 1983. They proved bounded generation for SLN over a ring of integers in a number field. And this holds for n at least 3. And actually, they proved bounded generation by elementary matrices, which are matrices with ones in the diagonal and just one other entry being 1. So, in particular, unipotent matrices. For n equal to, this holds if and only if this ring of infinite unit group, as has been proved by Morgan, Rapinchuk, and Suri in 2018. Somewhat classical examples of bounded generation for somewhat classical arithmetic groups. And let me make a remark that bounded generation allows, in particular, to parameterize polynomially the group SLN of this ring of integers. In the sense, what do I mean by parameterize polynomially? That there is a surjective polynomial map from in several variables that evaluated on the ring of integers produce all elements of the group in question. And we may allow here in the slides, they have only one polynomial map, but we may weaken the condition and allow a finite number of polynomials map. And I mention this because this follows trivially from bounded generation by unipotent matrices as for SLN O. So if we have bounded generation by expanding each power, we get a polynomial, and so we have trivially a polynomial parameterization. On the other hand, polynomial parameterization have been studied separately and independently. There was even an old question of Skolem about parameterizing SL2. And much work has been done. And for instance, even for n equal to, when we do not have bounded generation, except if the ring has infinitely many units, still there is a polynomial parameterization as shown by Wasserstein over Z, and then Larsen and Nguyen later recently extended to the remaining rings, also for n equal to. And this in particular shows that the polynomial parameterization does not imply itself the bounded generation. So there are two important properties that are quite related but not equivalent. And the result, last mention on a known result, the result by Carter-Teller was extended by Tavgan in 91 to all Chevalier groups of rank greater than 1 and to most quasi-split groups. So we have plenty of arithmetic groups with bounded generation property. And so these and some other results raised many mathematicians working in the field raised the expectation that the bounded generation property could hold in even rather greater generality. Now, going more specifically into the context of the work that I want to describe briefly, work in common, as was in the title, with Pietro Corbaia, Rapinchuk, and Jim Boren. We studied a case, so I have mentioned the generation of SLN was by unipotent matrices, but on the contrary, we study bounded generation with semi-simple matrices. And this would be needed for other potential applications of the bounded generation property. Indeed, there are groups which contain, there are groups of the type of GL and K that contain only semi-simple elements. So this is the motivation for concentrating on bounded generation with semi-simple. And I shall call anisotropic any subgroup of this kind. The usual definition is different, but it may be proved, although non-trivially, that it is for the groups in question equivalent to the one I am giving. So for simplicity, I shall call anisotropic any subgroup of GL and K containing only semi-simple elements. And I shall speak of the bounded generation only for these groups. So let me give some examples. A trivial case is the virtually abelian groups finitely generated by semi-simple matrices. That, of course, is, well, that is an anisotropic group, and if it is finitely generated, it is boundedly generated. Then other less trivial examples, definitely non-trivial, are, for instance, quaternions of norm 1 over certain rings of S integers. Again, here we have only semi-simple elements, and the same holds if we replace quaternions with other division algebras. And then another example I have in mind is the case of orthogonal groups of quadratic forms not representing 0. That is important. And that gives rise to anisotropic. Mayer's theorem, so we have to restrict to low rank, but we may get many more examples if we work over number fields or over rings like Z of 1 over n. So there is plenty of examples of arithmetic groups which are anisotropic. So I again go back as a remark to the former observation about polynomial parametrization. And in this case, if our group is boundedly generated by semi-simple elements, then the parameterization occurs, but with purely exponential polynomials. So this is a bit different, but there is a dichotomy in the theory also of Diophantine equations and other theories. Somewhat both kinds of objects appear polynomials on the one side and purely or non-purely exponential polynomials, as in the theory of linear recurrences. And let me recall, for instance, Matiasiewicz in the solution of Hilbert problem reduced certain purely exponential Diophantine equation to usual ones. And the same dichotomy appears on considering integral points on curves of genus 0, for instance. If the number of points at infinity is 1, then we get integral points with polynomials. And if the number of points at infinity is 2, then we may get integral points by exponential polynomials. And similarly in higher dimensions. So the polynomials are quite different from exponential ones, but there is this link, so to speak. And together with other observations, there was expectation that some non-trivial finitely generated anisotropic groups over rings of S integers would still satisfy bounded generation. So the object of the joint paper with Korvayer and Rapinchuk is to prove few results, which instead show that there are strong limitations to the bounded generation in linear finitely generated anisotropic groups. So indeed, the purely exponential polynomials lead us to quite different conclusions. So letters above to explain the results. In precision, letters above K be a field of characteristic 0, and let gamma in GLNK be a linear group. We have a first result, a theorem joined with Korvayer, Pinchuk, and Wren. If gamma is boundedly generated by semi-simple elements, then it is virtually solvable. So already this draws a quite strong limitation, quite strong conclusion on the group. And even if it is not anisotropic, so as soon as we have bounded generation by semi-simple elements, then we have a very strong conclusion. This conclusion, maybe let me make a few remarks on this result, that we may even allow one non-semi-simple generator. We have proved this bit stronger result with the same conclusion. And of course, due to the results that I have recalled before, like Carter-Keller, we cannot allow too many non-semi-simple generators because otherwise the conclusion becomes false. And now there is an open question, which is the maximum number of such elements, non-semi-simple, that we can allow in a bounded generation to draw the same conclusion. And the examples show that we can't allow more than 4. So we have proved that we can't allow 1, and still we have the same conclusion. We don't know already with 2. So this is an open question if somebody is interested. And let me remark that, so the theorem draws the conclusion that the gamma, if it is boundedly generated by semi-simple, then it is virtually solvable. But there exist virtually solvable finitely generated linear groups without bounded generation. We have an example that I don't recall for lack of time, but so this shows that a pure converse does not hold. However, if we also assume that gamma is anisotropic, then it may be proved through general theory of algebraic groups that it is automatically virtually abelian. So if it is virtually solvable. So it has bounded generation as soon as it has finite generation. So the following corollary in practice works. If gamma is anisotropic, then it has bounded generation if and only if it has finite generation and it is virtually abelian. Say that this result is a quick consequence of the previous theorem, because a finitely generated virtually abelian has bounded generation, and conversely, the theorem implies that gamma is virtually solvable, and we have just remarked that this property, together with an isotropic, implies virtually abelian. Okay, so in the remaining 10 minutes, I resume briefly the steps of our proof. So a first step is to reduce to linear group over number fields. So we let, for later use, also G, the Zariski closure of our group gamma. And we shall consider the Q algebra of regular functions on gamma, and we assume by contradiction that gamma is not virtually solvable, but gamma has bounded generation with semi-simple elements by contradiction. Now, to reduce to number fields, we first argue by specialization. So this G, this gamma is a subgroup of a certain algebraic, linear algebraic group G. So we may view it inside the GLN. And to reduce to the case of number fields, so the elements of gamma may be matrices with transcendental entries, but it is surely finitely generated by our hypothesis. So, the transcendence degree of the elements is finite. So the idea is quite simple and used in several other contexts to specialize through theorems like the Nustellensatz, essentially. So it is very easy to maintain, to find specialization which maintain the second property, so which keeps semi-simple elements into semi-simple elements. That is very easy. The first one is a bit more delicate, because we have to show that the whole group remains not virtually solvable. So there could be a degeneracy on specializing. However, one can argue with the derived series and use uniform boundedness of its length, which may be proved for virtually solvable groups inside GLN. So it suffices to show that the derived series preserves the length. And this is then again not too difficult matter by specialization to show that this degeneration does not occur at each step of the derived series. And then since it has bounded uniform boundedness, there is uniform boundedness, we can conclude. So we can argue from now on with a group with the same properties, not virtually solvable, with bounded generation with semi-simple elements, and defined over with points over a number field. So now a crucial step is this step on the existence of multiplicatively independent eigenvalues. So let gamma 1, gamma r be bounded generation for gamma. They are defined in GLN K, where K is a number field. And they are semi-simple. And we are also assuming that gamma is not virtually solvable. So a first step is to take the quotient by the radical of G0, the connected component of 1 in G. We take the quotient and we work in G prime in place of G. So we may further assume that by doing this, that G0 is a non-trivial semi-simple group. Non-trivial because it would be trivial if gamma would be solvable, virtually solvable. So at this point, we use a theory of Prasad and Rapinchuk, or theory of generic elements. And as a corollary of that theory, we deduce the following important step: the existence of an element of gamma such that its eigenvalues are multiplicatively independent from those of all the hypothetical bounded generators. So what we do, we take all the eigenvalues of the bounded generators, and they generate a group, a multiplicative group, a finitely generated multiplicative group. And what we prescribe is that there is, so we prove with this theory of Prasad-Rapinchuk the existence of gamma such that the eigenvalues of gamma are independent of this group. So no power of them lies in this group. No positive power of them lies in the group generated by the eigenvalues of the bounded generations. Let me here make a pause to remark the independence of values of rational functions. This is a part of the Prasad-Rapinchuk theory, and but there is a link, and then I want to remark this, with a completely different object of study, which sometimes is called unlikely intersections. And it concerns, for instance, torsion points on subvarieties of commutative algebraic groups and extended questions of the same shape. And so this multiplicative independence of values is not unrelated to theorems obtained jointly with Bombieri and Masser, and later refined by Guillaume Morin. So maybe that theory also can be applied to obtain conclusions similar to this. It is curious that a completely different theory of Prasad-Rapinchuk leads to somewhat similar conclusions. Of the setting and conclusion of my proof, we have obtained a matrix, gamma having an eigenvalue, not a root of unity, and such that denoting mu1, mu(s), the eigenvalues of the hypothetical generators, we have this intersection is trivial. Subvariety of tori. This is a deep theory. To apply this, we assume that each power of gamma is a product of powers of the gamma i's, which is would be ensured by the bounded generation. And now of course, by expanding, diagonalizing the elements, as we can do because they are semi-simple, we have identities like the one which is displayed. So a power of lambda is equal to an exponential polynomial in the eigenvalues of the bounded generators. So we in a torus, the equation. The subvariety is just y equal to the polynomial evaluated in x1, xt, and we have a point on that variety. And these varieties, these points, and this point is in a finitely generated group because the exponential equation holds with fixed lambda, nu1, nu t. And we have a theory that inside the subvariety of a torus, the points in a finitely generated group, their Zariski closure is a finite union of translates of algebraic subgroups, so isomorphic to tori. And this result is quite deep. It goes back to, it may be considered a piece of the Mordell-Lang conjecture for display, you see mentioned. And the origin of all of this is Wolfgang Schmidt's subspace theory. Anyway, with this result, it is not difficult to conclude because we apply the theory and would roughly conclude that this subvariety y equal to q x1 xt would contain, the points would be contained in a torus, and this would contradict the multiplicative independence that we have obtained by the Prasad-Rapinchuk. So I skipped the last comments that I had, and I stop here. Thank you very much for your attention.
Okay. Thanks a lot, Professor Zannier. I think you probably finished it even earlier than, oh no, half an hour. Okay, yeah. Okay, so are there any questions or comments people would like to share?
May I ask?
Yeah, of course. Yeah.
What is missing? What is such a result in characteristic P?
Yes, this is, thank you for the question. I really don't know. And besides, there are various steps in the proof, but even the last step, the application of this Diophantine stuff would lead to certainly to other cases and difficulties in repeating the arguments. So, so we haven't thought carefully at this situation, but certainly it would present difficulties in various points of the proofs.
Hello, this is Gopal Prasad. I would like to congratulate you for your great result, and I hope to read
Thank you very much.
your paper sometime once I am done with my current book writing, and really
Thank you.
wonderful achievement.
Thank you very much. I am flattered. Thank you.
Are there any further questions or comments? If not, let's thank the speaker again. Okay, it's all virtual, but yeah.
Thank you very much for the attention. Thank you.
Thank you.
The questions and the remarks.
Yeah.
Thank you very much.
Thank you, Professor Zannier. Yeah,